Hello everybody, my name is Tian Shixie. Today I'm so excited because I'm going to introduce a very interesting topic that is called playing Atari with deep reinforcement learning. So what's the Atari? That is a game company which has a lot of famous video games such as the Breakout, Pong, the Beam Riders, and so on. So our goal is to train a robot to play a video game like a human. So how does the human play a video game? We can think about that. So when we play a video game, first we will receive the visual information and then translate it into the sensory information. For example, if you are playing a video game and an enemy fire a bullet at you, how do you do? You're pressing the button to avoid against or use some skills like magic shout to protect yourself. Yeah, that's good. Maybe someone will say, I just choose stay there and do nothing. Yes, you can, but you will die in the game. So that's how the human play the video game. The question is, can a robot to play a video game like a human? The answer is yes. Moreover, it can surpass a human expert. So look at this picture. Here is a brain. We call it an agent. And first, he will receive some pictures information and then translate an action, just like press the button, and receive a feedback from the game machine. We call it the reward. And according to the reward, the agent will know the last action is good or bad. And reprecising this information to get a better action next time. So that's a roughly precise that describe how a robot to play a video game. So our method is to create a deep neural network agent to successfully play as many of games as possible. And this paper will present the first deep learning model to successfully learn control policies directly from high-dimensional sensory input by using the reinforcement learning. And we had applied this method to 7 Atari games from the arcade learning environment with no adjustment of architecture or learning algorithm. And we found that it outperforms all previous approaches on 6 of them and surpass a human expert on 3 of them. That's exact. So this model is to connect a reinforcement learning algorithm to the deep neural network, which operates directly on RGB image and efficiently precise training data by using the stochastic gradient updates. And we utilize this method that is called Deep Q Learning Network, DQN. And there are 3 important components. The first one is Q learning, and the second one is deep learning, is to recognize the image. And the third one is experience replay. In fact, that's a memory bank. So what's the Q learning? At the beginning, the arranged model is based on a table. So look at this picture. From the horizontal direction, it means the actions, and to the vertical direction, it means states. And each state is corresponding to a zero actions, and the robot can choose the best action which has the highest value. So that's enough to a simple game by using a table. But to a complex game such as the Go is impossible because the number of states is an astronomical number. So that's a challenge to the hardware or software or memory. So we have to introduce our model DQN that contains the convolutional neural network, which has the excellent performance in this domain. So here is the DQN algorithm. So first, we will initial the memory and the weight. And to the episode, it means how many times the agent plays the game. And you can define it by yourself. And for t equal to 1 to capital T, it means the game start. And this part is corresponding to 1 frame. So at the beginning, the robot selects an action and throw it into the game environment and get a feedback, and then store it as his memory, and then start learning by using the backpropagation to update its weights. 6. Pre-processing and model architecture. So why do we need to do pre-processing? That's because working directly with raw pixels can be demanding, as the number of states is an astronomical number. So we have to apply a basic pre-processing step aimed at reducing the input dimensionality. So the final input is an 84 by 84 region of the image that can roughly capture the playing area. And the first hidden layer includes 16 8 by 8 filters with stripe 4, and the second hidden layer includes 32 4 by 4 filters and stripe 2. And the last hidden layer is fully connected and consists of 256 units. And the last output is fully connected and with the single output for each valid action, and the number of the valid action between 4 to 18 on this game. Visualizing the value function. So here there are 3 frames. They are all corresponding to the point A, B, C. So to the first frame, you can see the Q value jumps because an enemy appeared on the left of the screen. And to the second frame, you can see the agent fire bullet at the enemy, and the Q value peaks because the bullet is about to hit the enemy. And in the third one, you can see the Q value fell to its original value because the enemy disappeared. Yeah, that's so vivid. So next I will run a demo, and I wrote the game and encapsulate the neural network to provide some interface that are very convenient to be called by my main program. And now I just write and and you can see the neural network can train the robot to play a video game. And in the final project, I will illustrate more detail. Okay. Okay, so first I will try this game. If you avoid the enemy, you will get 1 point. And after 5 points, you will level up. Okay, it's very easy game. Just use 2 buttons. Oh my god. Yeah, I choose do nothing. Yeah, so my highest value is 27. Yeah. Okay. Yeah, I'm going to try 1 time. Yeah. Okay, so next I will give the control to the robot. So it's difficult above level 5. Okay, that's good. So I think it has surpassed a human expert. It's, so it's amazing. Cool. And the highest, the max score is 10,000, nearly 10,000. Okay, because the time limited, so we stop here. Yeah. Okay, in the future work, I will continue to improve the performance from 2 aspects. One is overestimate and the speeding up training. So to the finger 5, you can see the original line, the right line has the high estimate value, and after using the double decoupling, you can see the result is the blue line is lower than the original one. And to the finger 6, you can see the blue one, which has the high time cost. And after using the prioritized experience replay, the result is lower. That's it. That's a red line is the result, and the difference is so clearly. Okay, conclusion. We have illustrated the deep reinforcement learning, and the detail include the Q-learning, DQ, and the experience replay. So in the final project, I will show how how the neural network train a robot to play a video game in the code, and how the game and the neural network interact interact. Okay, so that's exciting. And more fantastic contents will be shown in the next time. Thank you for listening.